All right, welcome everyone. My name is Sharon White. I'm the marketing manager for BLT. Welcome to today's webinar, Techniques for Space Applications, including the use of RFSoCs, ruggedized devices, and safe state machines. Before we get started, I just want to take a few minutes to introduce our speaker, Ellie, BLT, and to go over a few things. To get started, if you have questions, please put them in the chat panel. We will get to them during the Q&A at the end. Today's webinar is being recorded, and we will send that recording out once it's ready. And there are no books or slides provided with today's talk, but like I said, you will get the recording. So now let me introduce BLT and our speaker. BLT has been in the engineering design services business for over 30 years. And we were started by one of the original Xilinx FAEs. Our headquarters are in Maryland, where we are right now, and we also have an office in Melbourne, Florida. We design chips, boards, software, and complete systems for commercial, military, and intelligence clients, and our designs are in space, undersea, and everywhere in between. And we've been teaching AMD Xilinx training for 25 years. We're an AMD Premier Partner and an authorized training provider. Our training is by engineers and for engineers, and we bring our decades of real-world design experience to the classroom. If you're interested in events and services from BLT, be sure to follow us on LinkedIn, Facebook, Instagram, and the social formerly known as Twitter. We post all of our latest updates there first, so please check us out there, and I'll put a link into the chat panel for you. Today's webinar is being led by Ellie Rosen. Ellie is an engineering manager at BLT, primarily focusing on adaptive SoCs, RFSoCs, and MPSoC designs for both commercial and defense applications, and is one of our resident RFSoC experts. He is BLT's solution architect and lead engineer for all of BLT's space-related programs. And Ellie has spent many years managing AMD Xilinx-based FPGA projects, particularly for space, radar, and EW applications. Before coming into this role, he spent countless hours designing, integrating, and debugging radar systems, underwater sensors, and cryptographic ASICs. He's also a general tech enthusiast that enjoys playing with SDRs and home automation on the weekend. So welcome, Ellie.
Thank you, Sharon. I appreciate that. I appreciate you all being here today. And I do see a few familiar names in the chat from folks who joined us at the AMD Security Working Group last week. So it's nice to see you all again. So today we're gonna, go ahead.
Before we get started, Ellie, we got one more person on our team I want to introduce, if that's all right. So Lisa Weaver is on as well. She is our Senior Strategic Accounts Manager. If you have questions about our services, Lisa is your go-to contact. So I will put her information into the chat panel for you, and you can also reach out to her directly. Okay, Ellie, I will now pass it over to you. So go ahead.
Thank you, Sharon. So the way I like to have these webinars is, I'm more than happy to take questions throughout our conversation today. We're going to be talking for roughly about an hour on a few different variety of topics. The intent of this webinar is to really just give a surface level to the types of things that engineers should be aware of when they're designing for space applications. So to do that, there's a few different topics. We're going to talk first about what the RFSoC device is, how it operates as a monolithic integrated circuit, to do transceiver-based designs for RF, along with an embedded processing system. In that same vein, a part like this and other similar technologies, you may want to use this for, let's say, a low Earth orbit type design. And in those cases, one of the parts or devices that you may choose to use could be an UltraScale Plus XQ ruggedized device. So we'll talk about some of the features that come along with using parts like that. Then we'll switch over to the primary focus of today, which are some of the design best practices when designing for space. That'll involve techniques for optimizing for power, how to manage or mitigate events relating to possible data corruption and things like that when you're doing configuration and boot for the FPGA or the reprogrammable device. And then we'll wrap up with an example design and some techniques revolving around safe state machines. And so these are techniques to have your state machines be a little bit more robust to things like single event upsets, for example. So I will demonstrate that for you all in Vivado, and we'll leave some time at the end for any questions and answers. So just as an introduction here, the Zinc UltraScale Plus RFSoC is a single monolithically integrated device. For those of you who may be familiar with the MPSoC, that is a multi-processing subsystem. It has a processing system along with programmable logic. Depending on the device, you may either have a quad-core A53 or a dual-core A53 complemented with a real-time dual-core R5 processor, its own integrated memory subsystem, a platform management unit, which is used for booting the device, the configuration security unit, which is used for handling security and tamper events, as well as some system functions, the generation of clocks, things like that. Finally, the processing system also has integrated peripherals. Some of them are high speed, some of them are lower speed. An example of the higher speed protocols include DisplayPort, USB 3.0, SATA, and PCIe Gen 2 in the processing system. You can do PCIe Gen 4 in the programmable logic. There is support for gigabit Ethernet, either on the high speed or the low speed side. So that's just 1 gig Ethernet. And then some of the slower speed protocols, CAN bus, serial peripheral interface, SPI, SD cards or eMMC type memory, and NAND flash. On the programmable logic side, you have GTY transceivers that can support up to 33 gigabits per second of connectivity. This is for both transmit and receive. Depending on the device that you choose, you can have PCIe hard cores, hard IP, as well as 100 gig Ethernet cores. There's the programmable logic, which is based on the UltraScale Plus technology, which is a 16 nanometer architecture. And there's also built-in DSP logic, block RAMs, ultra RAMs that come with this architecture as well. Now, today we're talking primarily about the RFSoC. So the RFSoC is the similar technology to the MPSoC. However, it has an analog front end, and that analog front end has analog to digital converters and digital to analog converters. It also, for certain technologies, has what's called a soft decision forward error correction, which is typically used in modems and broadband communication. Like I said, the RFSoC is very similar to the MPSoC. The primary difference is that the MPSoC has a graphics processing unit, and it also in the EV devices has video codec units. The RFSoC does not have those primitives or peripherals, but it does have the RF data converter block, the soft decision FEC hard IP, and in the Gen 3 DFE devices has differential feedback equalization hard IP as well. Depending on the device that you select, there can be up to 16 ADCs and 16 DACs. The most commonly used device is where these DACs are actually interleaved for higher speed, giving you 8 ADCs and 8 DACs. For the purposes of this conversation today, I'm mostly going to focus on the RF side of things. Starting at the RF front end, looking first on the receive side. So analog signaling comes in to the ADC. That is a 12-bit converter. Then there are some 16-bit math functions, some gain phase compensation, complex IQ mixer, decimation stage, and a gearbox FIFO for either outputting IQ or real data. On the transmit side, your sample data is transmitted or sent from the AXI streaming interface in your programmable logic. This then goes through an interpolation filter if you choose to use it. There is a complementary IQ mixer with gain phase compensation for your IQ paths. This then goes to the 14-bit DACs that then are transmitted through analog signaling off of the FPGA. And then inside each of the ADCs in the DAC, each tile has an internal PLL, which can either be bypassed with a reference clock directly off the board, or you can use this to generate your sample clock in those tiles. Some of the advantages for using a device such as this, the number one case here is that there's reduced overall system power. So when you're having less components to support on the board, fewer power rails, lower voltage rails, the ability to turn on and off the various tiles, that will reduce your overall system power. Speaking in a similar vein to the BOM reduction of not having an external transceiver, as well as the other components needed to support external transceiver devices, you have a dramatic system footprint reduction with everything all encompassing in the monolithic integrated circuit. Just to address a few of the questions that are in the chat here, one of them is, what is the scope of the tamper event detection and mitigations supported? Not really the topic of today, but just to briefly cover, there is some power monitoring. The Versal devices have glitch monitoring capabilities. It really depends on the architecture. There's also system watchdog timers. I would invite that if that was a conversation you're interested in, that we could talk about that offline. There's also been some questions on the providing of the presentation material today, and we will always send you the recording of this webinar in a few days. Lastly, another question here on, are the RF ADC and the DACs on chip? And yes, they are on chip. They are all within a single monolithically integrated circuit. So back to the topic at hand. One of the nice advantages, in my personal opinion, of the RFSoC device is that as transceivers get to faster and faster data rates, the need for, you can no longer do an LVDS interface. You need to use transceivers to talk to external RF devices that typically uses the JESD 204B or C protocol. And it's not always straightforward to instantiate those interfaces. So one of the nice aspects of having a monolithically integrated circuit is that you're no longer responsible for instantiating the JESD interface. You are just given an IP in which you get an AXI streaming interface out of it. And it makes it a lot more straightforward to get a design up and running in short order. So switching gears here, I do want to talk a little bit about what are some of the design challenges when it comes to reprogrammable logic in space or low Earth orbit. So radiation affects devices in a few different ways. One of them is single event upsets. So a single event upset is when a charged particle maybe hits a flip-flop or a memory cell, and it flips the value of that memory cell. Maybe it was a 0, and it charged that memory cell to become a 1. So this would be appear to the FPGA as a bit flip. And so when a bit flip occurs, there's a whole host of things that can happen. In some cases, maybe it did a bit flip on a coefficient value that was being used for a filter. So then your math might be off by a little bit. That'd be like the best case situation that could occur. In other cases, it could, mess up your interrupt sequence to the processor, and you lose the ability to halt the processor. That would be, much more difficult to mitigate or correct in a situation like that. So there are some techniques that I'm going to talk about how to handle single event upsets, or living with the fact that we know that SEUs are going to occur. What are design practices to make them almost appear like they're non-existent? And then the other case here is the destructive single event latch-up. So single event latch-up is when radiation causes an IO pin, for example, to short from VCC to ground in the IO banks, or let's say the system monitor. And if that were to occur, that's going to cause, potentially an infinite power draw, which can damage the silicon. It'll cause a short, and it'll burn up the traces, for example. So there are some techniques on these ruggedized devices to be able to protect from that. And then when we're operating in a remote environment, how do we handle the fact that we can't just change the bit stream on the fly? When you're up in space, you're not going to just send someone up there to go and change that bit stream. So there are some architecture techniques that you'll likely want to implement in your designs so that you can load a new bit stream if something were to occur as one mitigation. And then in other places, you might want to have spare bit streams in case your external memory gets corrupted. And lastly, while the sun does provide or is an unlimited power source from the context of solar energy, depending on your orbit, if the Earth blocks the sun, then only about half the time will you actually, be able to charge your batteries. So being able to conserve power in space is very important. It's also difficult in space to remove heat generated from the device because we don't have the atmosphere to act as a conduction mechanism to extract that heat out. So minimizing power in those situations is important as well. Speaking to the single event latch up mitigation techniques, specifically for the UltraScale Plus devices, there are some impacts to the system monitor and the high performance IO banks. Now, there are devices, the UltraScale Plus XQ ruggedized devices, that can support extended environmental conditions. So when you're using one of these devices, there would be a new voltage rail where the voltage typically would just have a VCC aux pin. However, in these devices, the VCC aux is split between HD banks, the high density banks, and the high performance banks. The high density banks will still be powered at 1.8 volts. However, the high performance IO banks in these XQ devices, and if you are planning to use LV-aux, should be powered at 1.2 volts. When you power these IO banks at the 1.2 volts using the LV-aux standard, there is only 7 possible IO standards that become supported. Also, for these particular devices, if you are using the LV-aux capability and you would like to use a memory interface, your only choice is DDR4 memory. DDR3 operates at 1.8 volts. And so because it operates at too high of a voltage, you won't be able to use DDR3 when using the LV-aux setting. So your only option is DDR4. And basically the lower voltage is one way that AMD has mitigated single event latch-ups by operating at that lower voltage and then supporting memory configurations that run a little bit slower than the type of performance that you would typically expect on Earth. Here, the maximum DDR rate is 1.6 gigatransfers per second over the 1.866, and that's specifically because of the lower voltage. I'm also noting here that the options to enable this setting on your DDR is not available in the IP integrator. It specifically needs to be applied as a tickle command to your memory interface generator to turn that on. So AMD does have a user guide. The user guide UG584, that is a fantastic user guide that gives a ton of guidance on how to set up LV-aux, how to configure your designs, and the types of mitigations for single event latch-up. And as I said earlier, you're free to ask questions throughout this webinar if you'd like me to clarify anything. So I do just want to finally draw some attention here as a little disclaimer. So the LV-aux settings and the sysmon mitigations, these only apply to the XQ ruggedized UltraScale Plus devices, and they will only not latch up in certain LEO orbits. And so if this is something that you're interested in and would like to discuss further, our recommendation is to reach out to your AMD representative for additional details. When it comes to power saving, there's a few different techniques that you can take advantage of in AMD FPGAs. The most straightforward one is to enable power op design. And this is an additional optional step in the implementation process that will go through and implement a few techniques for gating clocks for block RAMs, or rather the clock enables for block RAMs when they're not being used, and some other techniques for minimizing dynamic power. There are a few things that as a designer you'll have to do to architect into your design. For example, ultra RAMs and block RAMs have various sleep modes. And if you would like to use those sleep modes, it's a bit that goes into those memory primitives, and you can turn those on to minimize dynamic power. It's often worthwhile to partition your design for areas that are always being used and areas that will only have periods of activity. The BUFG, the global clock buffers, do come with a clock enable pin, and so you can architect in your design a clock enable solution to minimize your clock propagating at certain times of your design. I do have a few questions here regarding single event latchups. So the question here is the Sysmon single event latchup mitigation described in UG584? And that is in that user guide. Another question here on, are latchup events destructive or recoverable with a power cycle? That I can't fully go into the entire details of that. It really, in some cases, it depends. There are cases where if you're able to catch the event occurring quick enough, but quick is a very relative term, that a power cycle could recover. There are instances where a power cycle will recover the device, but just keep in mind that these type of events are destructive. So if this were to occur, I don't want to give a number to how many times, but say, maybe one time you're lucky, and then the next time you power cycle, you recover, but say it's 100 times, not giving a number of when this would be, but at some point, it'll be destructive enough that the device will no longer work, or that pin will no longer work. And then there's another question here. I see that it's possible to disable Sysmon if not in use. Should this be an acceptable mitigation to the SEL, single event latchup? Miles, that's a fantastic question. That's something that we would need to discuss directly with a representative from AMD. Even if the Sysmon is turned off, the pins still physically exist, and so we would have to double check if that was a solution. It depends also on what level of disabling is done for the Sysmon, because typically it is monitoring the voltage rails for different boot up events and things like that. So it probably depends on the architecture to determine if that would be an acceptable mitigation. Following on the power optimization techniques, so using power op design, like I was saying, can potentially reduce up to 30% of your dynamic power usage in your design. Now, one of the reasons why this isn't on by default is because it does add some amount of time to your implementation process. So it is left as an option for folks that don't need it. Also, it can modify your design to do the clock gating and the chip enable gating for the RAMs. And so not everyone is comfortable with having the tool make modifications to your netlist. If you wanted to manually enter this command in the console, here's the syntax here. It is set power opt, and you can specify where you want the power opt. So if power opt design is set globally, it'll just apply it across the entire design, though you do have the choice to apply it to just particular hierarchies if you'd like, or exclude hierarchies. So it's very customizable. There's also the report power opt, and this will let you know what power optimizations were taken and where in your designs got the most benefit from those optimizations. Things as you can do as a designer for single event upset recognition. It is highly recommended for these types of designs to enable error correcting codes in your memories. So this would include DDR, high-speed serial I/O, SerDes links that support it, as well as your block RAMs and your ultra RAMs. What error correcting codes typically look like is that you have an extra parity bit for every byte of data. And based on this parity bit, you can correct for single errors and you can detect if a double error occurs. So sometimes you'll hear this called sec dead. Now, from an architecture perspective, you'll have to come up with a solution that collects all of that interrupt information from your memories to determine what your next state might be. So for example, say I have a block RAM that is impacted by a single event upset. When I get a single error, interrupt or a double error detection, that should then go to a processor, and then that processor will determine, do I need to reset my entire design? Do I need to reload that RAM? There could be a lot of different solutions that you might want to architect. Also, you can incorporate safe state machines. So if we want to ensure that a single event upset doesn't cause your state machine to get into an unknown state that doesn't exist, there are a series of synthesis attributes that can be provided so that the state machine is recoverable or doesn't get into a bad state. So for example, you can specify in the default state to flag an interrupt to the processor. And there's in the Vivado properties user guide, this shows the different options for the FSM safe state. And then also highly recommend that instead of having just a global reset in your design, that you segment your reset so that different partitions can be reset as needed if one of these events occurred, and this will help you save on time for recovery. There is a question here on if there's any differences in robustness between Gen 1 RFSoC and Gen 3, such as with respect to SEL, SEU on the RAM and the SEU on the block RAM. So my understanding is that the entire UltraScale Plus XQ Ruggedized series has the same level of tolerance and capability. So it's by architecture that determines that, not the generation of the device. There is also a question here about implementing TMR, triple modular redundancy on state machines. And I will come back to that later. I don't explicitly have a slide that discusses that, but it is a valid technique that you may want to use. When it comes to the single event upsets on configuration, there are a few ways of handling this. What this is referring to is if we have an external configuration memory, let's say a NAND flash, and there's a bit is flipped in that bit stream, what are some of the things that we can do to mitigate on the configuration of the FPGA or the external devices? So there's two IPs that exist within Vivado. The first one is the TMR triple modular redundancy soft error mitigation interface. So that is one example. There is also a soft error mitigation IP with a particular product guide here. And this will go through and review your configuration with the ICAP and will determine if there's been any upsets to the way the bitstream was configured. There are other opportunities for external scrubbing and other techniques, but that goes beyond what we're covering today. Coming back here to safe state machines, there are a few different definitions for how you can declare your state machines in your design. This is all coming from the user guide on the Vivado properties. So there are attributes that you can apply in your VHDL or parameters in your Verilog to specify these different types. The first one here is the reset state. So this will make sure that your state machine will just be in the reset state based on how it's configured, so that when the device powers on, whatever I set my reset state to, that's what will power on with the state machine. The next one is the power on state. So the power on state, this is how you declare the signal type for the state machine. You can have a separate power on state from your reset state. In AMD FPGAs, they always come up in a known state. That's your power on state. So the power on state, I can set potentially a separate power on state from my reset state. The reset state would be like if I have if reset equals 1, that's the reset state. Power on state would be based on how my signal is declared. Then we have the default state. So this is that the machine, the state machine, if it goes into an invalid state, that it will go and follow whatever is in the default state. And then finally, we have auto safe state, which I'll show an example of today. And that will do a Hamming 3 encoding that can correct single bit errors on your state machines. So this is similar to the question here of triple modular redundancy for state machines. Here we're using a Hamming 3 encoding, which gives you a similar type of behavior. It's not voting based. It's an encoding that makes sure that you're in the right state. Now this is synthesis attributes. So these are things that just by incorporating these attributes, the tool will give you different devices. I do have a question here on power on. We expect the device to be in reset. Why do we need a power on state? That's a great question. For AMD FPGAs, it is not always the case that you need to provide a reset for every flip-flop in your design. AMD guarantees that FPGAs will always turn on in a known state. That's the power on state. This is where after GSR, the global set reset is deasserted, but it is not guaranteed that a designer will include a reset on every flip-flop. You don't always need a reset on every flip-flop. And so that's why there is actually a difference between your power on state and your reset state. But that's a really good question. So here's just an example of what this would look like in VHDL or as a tickle property. So you have two choices for how you'd like to do this. In the VHDL example here, I have a type called count state, and it has the states from 0 to 7. Then I have a signal that is of the type count state. I'm declaring my FSM safe state attribute, and then I'm applying that safe state attribute to the my state signal, and I'm specifying that I want the power on state option. As another example, I can have a tickle command or a constraint that says apply FSM safe state, give it the reset state, and then you're giving it here the cell, which is the register for your state machine current state. So for my example that I'm going to provide today, I took just a very basic 4-way intersection state machine that is controlling, whether or not the traffic lights are, turned on and who has right of way, things like that. There's nothing overly complex about this state machine. It's mostly just a timer. It's not taking inputs from, that there's a car present, things like that. It's just looking at, based on time to change the traffic light. So if I move on over here to my Vivado environment. So just at the high level, here everyone can see I have a top. The schematic is of my top, and I have my outputs that specify the states that were shown on the previous slide. The top ones here are all for the first state machine, and the second one here is for the second state machine. So I have the same state machine, but I instantiate them twice. If I show my top file here, here I have the two state machines. The only difference between the two state machines is that one of them is safe, and that it's using the safe state machine attribute, and the other one is just using the default state machine. If I then show the state machine, it's a very straightforward state machine that has a counter, and then after some number of clocks, which equates to wall clock time, it transitions to the next state. So the only difference, we're using the same VHDL module for both designs, but the only difference here is how we're specifying this safe state attribute. So this is set to a generic, and we are changing this generic based on how it was instantiated. Now this actually does implement very quickly, but I already pre-did it before the webinar. And what I want to show here is I've specifically extracted from the netlist the registers for the safe state machine. So on the top here, we have the safe state machine that's using the auto state controls. And on the bottom one here, we have the default one. So if we take a look in the netlist and we look at the leaf cells, we can see here that in the default one, it is using the sequential state. Whereas in the safe one, let me just minimize that. In the safe one, we are using a Hamming 3-state logic. So there is, slightly more hardware added when you use this implementation, but it does make it a little bit more robust to single event upsets because it is able to correct for invalid states. All right. So really, my goal of today was to showcase a series of, different techniques, different ways to start thinking about how you might want to architect your space-based designs. Obviously, triple modular redundancy is very important, but when you do that, you increase your device size or your module size by 3 times. So that's not always the answer for every aspect of your design. You might run out of lookup tables. There's also some floor planning concepts that are important. For example, if you're doing a TMR design, you don't want to place each item of your TMR in the same area of the FPGA as just another straightforward radiation mitigation technique. One of the things that we can also see here, if we just look from the number of cells, you can see that the default case only has 60 cells, whereas the safe one has 15 extra primitives. All right, so with that, does anyone have any questions? So I do have one question here. Can I explain the difference between the Hamming and traditional TMR? So Hamming is a encoding scheme where you have parity information with the with your data. And so if a bit gets flipped, it is able to use that parity to go back to the correct value. So, if there's only a single bit flip, then we can correct for that single bit flip and get back to the state that we would like to. Now, TMR, that is where you are replicating all of your logic 3 times. So I would take the same state machine, I would replicate it 3 times, and then I would vote on the answer. So that would have significantly more hardware associated with it. In this case, we're just making sure that we're not leaving the wrong state.
So Ellie, before you get to more of the questions from our attendees, I know we did an RFSoC or RFSoC, depending on how you call it, project last year that was for LEO. Do you think you could talk a little bit about that?
Yeah, absolutely. So we've done some work here with RFSoC designs and low Earth orbit designs, and so many of the techniques that I've talked about today kind of just come from some of those best practices. It's partitioning your design with resets, having a software API and mechanisms to collect all of the error correcting codes to make sure that there aren't single event upsets propagating through your design. Power mitigation techniques because we don't have unlimited power or unlimited heat dissipation. Those are all the types of things that we've done for folks in the past.
All right, we have a ton of questions coming in, so go ahead.
Sure, I'll start going through some of them here. The next one I got here is, how do you report that the FSM transitioned to an illegal state? So that's a very difficult question to answer. In some cases, so the state machine itself is not going to report that it's in an illegal state. However, typically synthesis tools will actually ignore the default state because it's not supposed to be, you're supposed to have every option of your state machine supposed to be a possible transition. So if we don't have every possible transition, we can program a default state. And so if a single event upset would occur, we tell the state machine to go to that default state. And in that default state, we can create a flag and have that flag go to a processor to say, hey, I went into an invalid state, and then try to recover from it. Another question here, can I explain a bit on how a safe finite state machine is safer? If I understand correctly, you can't go into the wrong state if there is a single event upset. So just as an example here, if typically the Vivado tools use sequential encoding for a state machine. So if I have a 8-state machine, I need 4 bits to comprise of that of the state variable. And so if I'm only using 8 states, that means that there is 7 other states that are not valid states. And so if there were a bit flip that could then go to that invalid state, there'd be no way to recover. However, if I use the safe state machine mechanism, that would prevent those states from being possible, or to have a state that it transitions to if that event were to occur. Can you compare safe FSM with default FSM when there is a single event upset? So for example, if you have just a regular non-safe state machine, the default case will be ignored. And if there were a single event upset, then you would go into a state where potentially you could have 2 states executing at the same time, or you could potentially have a state that just has no other way to transition to another state, so the state machine would just get locked up. So those are the things that can happen. So when you use the safe FSM, that should prevent from the situations where you get into unreachable states or ways where your state machine will get stuck. Another question here, ISE used to have a TMR tool that helped with TMR. Is there anything like that in Vivado? There is not a explicit TMR tool in Vivado. You're mostly on your own to instantiate your IP or your HDL multiple times and create your own voting capability for that. Is there a Vivado synthesis property or attribute to automatically do TMR? So like the previous question, TMR is a system architecture specification. And honestly, you probably wouldn't want the hardware or the tool to automatically infer TMR because you'll have a very large design. So from an architecture perspective, you'll typically want to come up with the places that the TMR would be important rather than do it for your entire design. in a TMR design, if we physically place logic, will the voting logic become prone to glitching? And that is possible. It's an architecture based way on how you decide to do this. Typically, if you make things further apart or greater distances between the TMR devices and your voting, you're less likely to have those effects. But the effect can, if you have the radiation particle go across the device, who knows what it could have touched. So it really comes down to system architecture and how you place everything to ensure that it won't be a problem. At least in ultrascale. I did hear in that in Versal, there's some techniques based on that architecture where the placement is no longer actually as important versus ultrascale. Another question here, is there a way to TMR Xilinx or third-party IP? And so for situations like that, you would have to instantiate multiple copies of that IP as long as it's not consuming hard IP. So any soft IP, you can make 3 copies of and vote on it if that was important. The talk today has been MP-SoC generic. Do you have any specific comments on radiation effects on the RFSoC? I don't have anything specific. The RFSoC devices, being as that they're part of the UltraScale Plus family, they just have the same radiation tolerance that comes with the XQR architecture for the UltraScale Plus. Do you have a question here on if I could talk about the Sysmon issues and their mitigation? My understanding for the Sysmon is that there's the possibility that the Sysmon can read the same value multiple times where it gets stuck at a particular value. And there are some techniques listed in that user guide for how to mitigate against that, specifically the lower voltage, for example. But how it presents itself in Sysmon, the Sysmon as an ADC, a lower speed ADC, it should always report a different value every clock cycle. And I've found that if it were to report the same value for multiple clocks, that is a good indicator that there might have been a latch-up event. Another question here on if increasing the Hamming encoding order, is there a point at which increasing it further is counterproductive? So really, that's based on the project that you're working on and what their requirements are. A lot of this comes down to when you're doing an analysis on MTBF, or mean time between failure. So if you have requirements that your MTBF needs to be like 1,000,000 years, then increasing the Hamming distance makes more sense. However, if you can go shorter periods of time for the MTBF, that can potentially dictate not needing to have such a high Hamming distance. So really, it's an architecture decision based on your system requirements. Do you have any recommendations for making the processor side of a design more robust? So that's a little bit difficult to answer. The main pieces here are including code that will scrub your instruction data in the DDR. That can help make it more robust. Having watchdog timers, so using the watchdog timers that this is supposed to occur every second. So if that weren't to occur, then that could potentially indicate that a single event upset occurred. So those are probably my best recommendations for how to handle things like that. Is the Hamming code safe FSM method more efficient with respect to area and timing compared to TMRing the state machine? So whenever you do TMR, you are triplicating your logic. So when you triplicate that logic, that's going to take up significantly more area and more power. Whereas if you use the Hamming methods, that is encoding the data to resolve that, so that's typically less area and more efficient. But there is no TMR attribute that can be applied to the registers. There is a question here: is there a relationship between clock rate and SCU susceptibility? I don't believe there is a relationship there. The particle, comes like in an instant. The how much it charges that flip-flop, for example, doesn't matter what frequency you're operating at. It does affect, if you're running faster, it'll crash your system faster, but it's not, the event occurs. It's an event. It's not a period. And then also there's a really good question here on separating resets. So obviously you want to always use synchronous resets within your designs, that there should be no asynchronous resets in your designs. And so typically, you may have an asynchronous reset coming into the FPGA, but then it should be synchronized to all of your clock domains and then used synchronously throughout the rest of the design. Sharon, are there other questions that you think I'm missing here?
There's a couple that we actually had from the registration forms. So when you guys register, if you put questions there, I do collect them. So one of them is, what is the best practice to use Xilinx IP in space applications? For example, is there a way to use TMR general Xilinx IP? I think maybe you answered some of it, but maybe you can answer that question.
Sure. So when it comes to TMR with the IP, obviously you can always instantiate your IP multiple times, as long as it's not using hard blocks, because if it uses the hard block, it's consuming that. So for TMR, you can instantiate that IP multiple times and then create your own voting circuitry.
All right, and then we have the question, what is the main difference between the RFSoC and SoC in terms of FPGA resources and peripherals? Is the fabric the same? Is it correct to say that all HDL logic implementable in an SoC is also implementable in an RFSoC?
Yeah, so that's a great question. What I believe that's referring to is, in an RFSoC, which is based on the UltraScale Plus architecture, that is similar to the MPSoC, which is also similar to just an UltraScale Plus FPGA. So all of that is the same architecture. Any hardware that you write to target the UltraScale Plus architecture will work in any of those parts. Also, if you write your code so that it can be inferred, so that you don't instantiate DSP slices, for example, it can also be used between other generation architectures like Versal and 7 series as well.
All right. If you guys have any more questions, please put them in the chat panel while we're waiting to see if there's any more. Ellie, maybe you can explain to folks if they have more questions or they want to take a deeper dive into these things, where can they learn more about this?
Yeah, absolutely. It's funny. I do get asked, if we offer any training for space type designs, and the challenge here is that it's typically so architecture specific and specific to what people are looking for, that we'd actually do two things to try and help folks with that. We have something called an experts exchange, and that's where some of the BLT engineers can actually go on site and work with folks on their problems to determine how they might best architect their design. And then also AMD recently announced that BLT is going to be a coaching service provider. And so as a coaching service provider, that gives us the opportunity to do somewhat of a customized training with folks to specific topics. And so if folks do have an interest in space applications and how to architect solutions for this type of stuff, that's a great way to get an introduction and get more in-depth information.
All right, I'm going to take this moment. We have another question that came in, but I'd like to plug some of our other webinars coming up, including one that Ellie is going to be doing in January, which is on the closing time using intelligent design flow with a spotlight on the AMD new tool feature. So if you're interested in that, I'll put the link in the chat panel. And we also have a complete webinar series, and I have the February dates already published on our website, and the rest of 2024 will be coming out shortly. So keep an eye on our website for upcoming webinars and our 4-hour workshops, which are no-cost events. They'll be posted there soon. So Ellie, I'm going to kick it over to you for the question.
Yes, there is a question here. The question is whether or not we did an analysis of with these devices up in space to determine and detect the SEUs and the SELs. And for the particular projects that we've done so far, we did not bake into that solution mechanisms to do that reporting. Mostly the work that was done was for prototyping and for proof of concepts. And so it wasn't important to measure those metrics, though the designs are working as expected. And I do have anecdotal information from other designs. It's not, there isn't always time in the schedules to factor in the measuring those types of metrics for some of those designs. So unfortunately, we didn't do that for those designs.
All right, are there any other questions? All right, well, we appreciate everyone joining us today for this look at space applications. Ellie, we really appreciate you sharing your expertise with us.
Absolutely, and if there's anything that anyone would like to discuss afterwards, you can always reach us at info@bltinc.com, and you'd be able to reach myself or Lisa. So I appreciate you all joining and being here today.